So a little review. I know you've seen this before. Um, so the quadratic formula. I mean, the best way to solve a quadratic equation is by factoring. I think it's quicker, it's easier, but that only works if you have nice rational zeros, or the integers or their fraction. When they're irrational, and that's what all these problems that I picked here are, and then we get down below, they're complex even, so imaginary solutions. You kind of need, I mean, you could do this by completing the square, but that's kind of gone passe. I mean, people still like it and they learn it, but I'm going to show you the quadratic formula. So you probably remember, now I got to get this pencil working, all right? Let's see. There we go, that's better. X equals, because we're looking for where these graphs cross the x-axis, right? Where these functions cross the x-axis. It's negative b. You change the sign of the middle term, the linear term, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. Plugging this in is the easy part. Simplifying it's the hard part. And just so in case, I mean, maybe you're wondering what the heck's a, b, and c. Ax squared plus bx plus c has to equal 0. That's the quadratic formula, a quadratic equation we're solving. A, b, and c are just the numbers in front of the terms, or the coefficients, right? So let's look at number 10. I see number 10, I see a equals 2, b equals 11, c equals 1. So let's just drop it. I don't think it factors. I mean, there's no way I could factor 2 and 1 and get 11 in the middle. So I know I got to use quadratic formula here. So I'm going to change the sign of the 11 because that was positive. Plus or minus the square root. Now I'm going to do this because I make fewer mistakes when I do this. I see how it says b squared here. Let me do a pointer so I don't mark it all up. Now, where is it? See how it says b squared there? I'm just going to take that 11 and I'm going to square it. I'm going to write 121. That way I don't have to worry about squaring it later. I'm not making an order of operation mistake. Then I'll do minus 4 times the a number, which is 2 in this case, times the c number, which is 1 in this case, and that's all over 2 times 2. Okay. Now we're going to work inside and get that to be one number. So I've got 121 minus 4 times 2 times 1. Well, order of operations says we got to multiply before we add or subtract, so that's 8. So 121 minus 8 is, let's see, it must be 13, right? 113. So I'm going to get negative 11 plus or minus the square root of 113 all over 4. This is let me make sure that looks like a 13 so I don't make a mistake and you understand what the heck I'm doing. So then what I've got to do to get an exact answer, that is an exact answer. Sometimes we're going to simplify it. Now I think that 113 is prime. I don't think that breaks down. Um, let's see. I know it's not divisible by 3 because 1 plus 1 plus 3 is 5, so that means it's not divisible by 6 or by 9. It's certainly not even. I'm pretty sure that's a prime number. So I think we're done right here. Now, if this were a math question, they might be looking for something like this. They might be looking for negative 11 over 4 minus the square root of 113 over 4. That's one solution. And then negative 11 over 4 plus the square root of 113 over 4. So if this were a math question, they'd probably want the answers like that for an exact value. Okay? Now, if you want, you can stop the video and go ahead and number 11, number 12 should be the same because I had it do uh, sets of 3, so they're different. Because you see number 13 is a little different. I'll stop and do that. If you download this handout, the answers are on the next page. Not the how to do it, but just the answers to help you out. Okay, so here, let me stop this video a minute. I'll go down and do a couple more, and then I'll do what happens when they're not equal to 0, because everybody makes that mistake. Not everybody. There's more than one that does. Here, let me stop let me stop. So when you get to a question like this, we always want to have that quadratic equation set equal to zero because we're looking for when is it zero. That's what the quadratic formula does for us. So I've got to move that negative 2 over. So I'm going to rewrite this equation as 7k squared minus k. Now I got to add plus 2 to move it, right? So minus 2 equals 0. Now I'm good to go with the quadratic formula. I mean, it doesn't factor because I can't get 7 and 2 to combine to get 1. So A is 7, B is -1, um, C is -2. And we'll see what happens with this now. So X equals, I'm bad about doing that, negative B, so negative, 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 -1, because -1's in the middle, that turns +1. So I'm going to go back and just erase that, but I didn't want to just throw it in there without seeing it. So 1 plus or minus the square root of 1 squared was 1 minus 4 times 7 times -2 all over 2 times a, which is 7. So I'm going to go 1 minus 4 times 7 times -2. Well, that's going to be 1 minus 28 times 2 is 56. So it's positive 56. And then I'm going to add that I get 57, which again I think is a prime number. So x equals 1 plus or minus the square root of 57. Well, actually isn't. It divides by 3, doesn't it? Because that adds to 12. I'm getting ahead of myself. Over 14. Well, let's see what happens. I know it divides by 3. Let's see. Can I move this down? Can I move this all down? Here, I can move that down, move that down. So I know that 5 plus 7 equals 12, and I can divide 12 by 3, so I know it's divisible by 3. So let's see. I don't know if I can do this in my head this morning. Oh, like that goes in once. I'm going to have 27 left over, so 19. Well, 3 and 19 are both prime. Neither one's a perfect square. I'm done. I don't have to simplify it. But you got to check. And so we're done. If we want to make my open math happy, 1 minus the square root of 57. Oh, so we do 1 over 14 minus 1 over root 57 over 14. And then the other answer is 1 plus 57. Oh, and both of those have to be over 14. Okay, so set them equal to 0, throw it into the quadratic formula. So let's look at number 15 now. The whole reason I made this video was about the complex numbers, but I thought I couldn't resist doing the other rest of it. So a quadratic equation that's not equal to 0, we got to bring the 9 over, so I'm going to add 9 to both sides. So I've got 2n squared minus 12n plus 9 equals 0. I don't think it factors. In fact, I know it doesn't factor, so I won't even try. I usually do try first because the factoring is so much easier. So I know that a equals 2, b equals -12, c equals 9. So it's negative b plus or minus the square root of b squared, 12 times 12 is 144, minus 4 times 2 times 9. Actually, now I'm looking at this. I don't think this is going to be an imaginary number, but I'm pretty sure it simplifies, and that's why I grabbed it. So it's going to be 2 times 2. And now we do the cleaning up. 144 minus 4 times 2 times 9. 144 minus, let's see, what's that? 8. 8 times 9 is 72, which that subtracts to 72. So I've got 12 plus or minus the square root of 72 over 4. So now I see 72, and I'm looking for numbers that are perfect squares so I can factor them out. And I know that 36 times 2 is 72, and 36, right? The square root of 36 times 2 is the same as 72. The square root of 36 times the square root of 2 is what, so we can take the square root of a product. And so that becomes 12 plus or minus 6 square roots of 2 over 4. And then what this allows us to do is, if you think about what my up and math's looking for, 12 over 4 plus or minus. I know we should be writing it out that twice, but I'm only going to write with a plus and minus. 4 times the square root of 2, and then 12 over 4 is 3 plus or minus, and the 6 over 4 is 3 halves. So I'm going to write 3 square roots of 2 over 2. That's a 3 right here. And that simplifies. I mean, we could certainly do something like this. We could say, I don't, why would we want to do that? Let's leave it just like that. Okay, so that's that one we had to simplify. And again, some more just like this, probably 14 and 16 are the same. Okay, so here's one last one for this video. It's getting too long as it is. But so we got to set it equal to 0. 8p squared plus 7p minus 1. Sorry, I'm going to add 3. So that's going to be not minus 1, but it's going to be plus 2, isn't it? And then we know that a equals 8, b equals 7, c equals 2. So -7, negative b plus or minus the square root of b squared. 7 times 7 is 49. Minus 4 times 8 times 2 all over 2 times 8. So let's go underneath. 49 minus, let's see, 4 times 8 is 32, times 2 is 64. Oh, we're going to get a negative number, so that's a flag that this is going to have two complex solutions. Something we're going to learn during week 5 is that if I have one complex solution, there's going to be two, because they come in conjugate pairs, it's called. So negative 64 all over, oh, sorry, I didn't do that right. 49 minus 64 is negative 15, is it? Over 16. Now, I can't take the square root of a negative number, so that's where the I comes in. I for imaginary. So here, let me write plus or minus. Plus or minus. I square root of 15 all over 16. And that's not going to clean up anymore. That's we're done. But that's how you deal with the square root of a negative number. So pay attention to those. Sometimes you'll have something that once you pull the I out, you've got something here that something here that can be simplified. Sometimes it's a perfect square. You can just take the square root of it and write something I, or you got to break it down like what I did earlier by like that 36 times 2 problem. Okay, I hope this helps you. This is all we need to worry about for complex numbers too, is this. It's theory. The theory says there's supposed to be two zeros for this polynomial, and because the exponent's 2, and if you were to graph it, or if you were to graph this here, it would never cross the x-axis. It would something like, what the vertex? I don't know. I'm going to fake it. It would look something like this. It'll never cross the x-axis, but we got to make the theory work. And the theory is that there's, like I said, two answers here, and there aren't, so they're imaginary. Okay. I asked my engineering brother where he ever used complex numbers. Specifically, it was the trigonometric form of a complex number. And he said in a magnetics course, a magnetism course, that all differential equations that have complex solutions that have to be written in trigonometric form. So I've never taken that course, but if you're heading that route, that's where you're going to go. All right, give me a yell if you need some help with this. If you want, you can go back and do some more of those exercises, as I said, and get the practice if you need it. Make sure you can factor.